Hello and welcome to this Aerospace Testing International webinar today with Lunar Innovations. The title of the webinar is High Resolution Non-Contact NDT with Terahertz Technology. I'm Ben Sampson, editor of Aerospace Testing International and your host for this webinar. The use of terahertz technology in NDT is growing thanks to its high resolution and safe non-contact operation. So I'm pleased to say we have with us today presenting one of the leading experts, if not the leading expert in the field from Lunar Innovations, Dr. David Zimdars. Hello, David.
Hello.
Hello. Great. Good. Thanks for taking the time out to present today. I'll just say a little bit about you and a little bit about the format of the webinar, and then we'll get into David's presentation. So David is director of terahertz contract R&D at Lunar Innovations. He's managed all of the R&D into terahertz systems at that company since 2001, and slightly before, I think you said, David, before from its kind of early days. So he has 10 patents and has published over 85 articles in this area. So David is going to start his presentation, which will run for as long as it runs. During that time, I would encourage you to please post questions via the box on the right-hand side, your Q&A tab. You won't see those questions immediately. It's not a chat button. But what will happen is after David's presentation, as I give him the questions, I will publish the questions and everybody will get to see them then. But I would encourage you to get your questions in as they occur to you, because what happens a lot of the time is people wait until the Q&A session and then we can run out of time quite easily. So David, thanks again for giving the presentation today. Over to you.
Hi, so I'm David Zimdars. Thank you very much for attending. I'm going to start off by giving just a little bit of an overview of Lunar Innovations. Lunar Innovations is a publicly traded company that has its headquarters in Virginia. I'm actually located in the terahertz product division is in Ann Arbor, Michigan, which you can kind of see in the central United States there. But the company has a number of different sales and manufacturing offices for different product lines throughout the world, including the United Kingdom. So I work particularly in what's called the lightwave division, which is structural material test and process control, so non-destructive evaluation. One of the other larger product lines is fiber optic strain gauge measurement systems. But we are specifically talking today about terahertz measurement systems. And we also do a large amount of contract R&D. In my specific case, I've worked for years developing applications for terahertz technology for the military industrial processes. So this is just an overview of Luna product lines. There's the fiber optic sensing, photonics communication test, lasers, and so forth. But I'm specifically going to be talking about terahertz gauging imaging today. So I'm going to also then next move to just a little bit about how terahertz non-destructive testing and measurement works. And I think the simplest way to think about this is that it's a non-contact electromagnetic analog to pulsed ultrasound. So the electromagnetic impulses are emitted in the terahertz region. So essentially, we emit an impulse that if you were to then take the Fourier transform of this electromagnetic transient, you would get energy between about 50 gigahertz and 3,000 gigahertz, up to about 6,000 gigahertz, depending on the system, although most of the work that we do is between 100 gigahertz and 2,000 gigahertz. Again, this is just a little bit of a graph to show how the interrogation works. So if you look on the upper right-hand corner, you've got a center, and there's an impulse shown in green that's going to interact with a multi-layer stack of materials, okay? And what happens is the pulse interacts with the first interface, And similar to an ultrasound pulse, you get a reflection off the first interface because you're going from an air to a material, dielectric material, and the speed of light changes, it decreases. And then if you then hit a second interface inside the material, you'll get another reflection pulse. And then you continue to travel through the material, and you can get multiple reflection pulse each time you get a change in material. And the instrument then records in reflection waveform consisting of the series of reflection pulses, which can be positive if you're going from a medium where the index of refraction is going from low to high, and then negative if it's going from high to low. And if you're familiar with an ultrasound A scan, this is very similar, except of course we don't require any kind of contact. One big difference is, though, it is electromagnetic, so as soon as you hit metal or purely conducting material, you stop. You can't make measurements. So this is very useful for measuring dielectric materials like imaging through or measuring the thickness of coatings, specialty coatings, paints, insulation, thermal protection systems, non-carbon fiber composites, glass reinforced composites, and I'll show examples of several of those applications throughout the presentation. So one of the primary things that we measure is the thickness between layers and structure, so that you can calculate that essentially by measuring the time of flight between the reflection of two layers. And again, we can measure down to down to easily less than 10,000th of an inch, and actually down to microns, depending on the material. And this is because of the extraordinary high time resolution of the waveform. We're literally measuring the speed of light as you're going through millimeters to microns thickness of layers of material, the difference in that. This is just a screen showing what the instrument does in sort of an intermediate processing level, where you would get, say, one reflection pulse and a second reflection pulse, and we're setting up a recipe to calculate the time of flight between those two, so you can calculate the thickness, say, of this material. Our instruments essentially have this sort of very sophisticated software that allows you to set up this waveform analysis that can happen depending either 100 times per second or 1,000 times per second, depending on the waveform acquisition rates. But we have industry-leading waveform window lengths where we're acquiring the greatest range, which works out to, say, in the air from up to about 4 inches worth of depth. Although the working distance can be longer, the window is centered on about 4 inches. And then waveform acquisition up to 1,000 times per second. So some of the advantages here is that you can measure multi-layer materials. It's non-contact. You can look for things like voids, bubbles, delaminations, buried defects. You can measure the thickness of wet coatings. Okay? So you don't have to contact them yet. You can measure them as they dry. You can predict wet to dry thickness. And you can also do both spectroscopy and frequency domain measurements if you like. It is unlike radioactive methods or X-ray methods. There's no radiation involved, no ionizing radiation. Again, unlike ultrasound, you don't have to contact. If you are doing eddy current gauges or magnetic measurements, it is not sensitive to curvature of the substrate or the substrate material, so you don't have to calibrate a witness coupon, say, for measuring the thickness of materials. Just as an overview here of how the products are configured, We have essentially what is in the center here, that box shown called Terametrics, which is our product name, a brand name for the products. That's what we call a terahertz control unit, which includes a laser system that helps trigger the terahertz generation and detection remotely through fiber optics to a sensor head. This, the center one, is an industrial application for, say, measuring the thickness of plastic sheet or insulation on as it's coming through an extruder. So that sensor, which is inside the loop of cable, there would be mounted, say, on a gantry that would be scanning over the surface of the extruded product. We do laboratory non-destructive testing. So in the upper left-hand corner, you see something, a C-scan imager. And then we have more portable or factory-level non-destructive testing, quality control, where we have a handheld thickness probe, which is shown there, and also a handheld B scanner device, which allows you to get B scan or cross-sectional images, as well as two-dimensional C-scan images of your target. So here's just another picture of the handheld probe unit system set up. That fiber optic umbilical cable can be up to 45 meters in length, so well over 100 feet in length in distance. We have different sensors, some of them which are Class 1, Div 1 certified. The EU terminology is somewhat different, but that essentially means that it can be used in flammable environments or around previously fueled aircraft. This is just showing, again, some more of the applications. The upper left-hand corner, thickness measurement being used to measure specialty coatings inside an inlet duct, transmission spectroscopy in the lower left, 2D scanner for C-scan image in the middle bottom. We have done measurement of bottle wall thickness, which is not necessarily aerospace application, but examination. And then what we would call the line scan gauge, which can either make cross-sectional B-scan images or 2D images. This is just an overview of the various terahertz sensors. I think the most interesting one is the lower left-hand one, which was designed to be mounted on paint robots and is Class 1, Div 1 certified, so that it can be operated in explosive environments, or not explosive, but say flammable environments, where you have making the terahertz measurements through the paint spray plume, which of course would have a lot of evaporating flammable solvent at the same time. So here's some various different applications we have had. Measuring the coating thickness on aircraft. This ranges from standard paints to very specialty coatings applied to military aircraft. Cross-sectional imaging of these coatings, looking for delamination and defects. Measurements of thermal protection systems. The lower right-hand corner is actually a test panel that was used on the Space Shuttle external tank thermal insulation system, so imaging through that to look for voids and disbonds inside that, and then we continue to inspect spacecraft thermal protection systems. One of the first applications I'm going to talk about is the measurement of the thickness of aircraft coatings, and particularly specialty coatings, which are often very, very thick. They may be up to from 20 thousandths of an inch thick up to 250 thousandths of an inch thick. Getting into the centimeter range. And you have to have pretty tight tolerance to the thickness. In many cases, the coating applications take several days to apply and cure. Traditional non-destructive thickness gauges like UT and eddy current require contact, so you can't really use that for wet coatings. Destructive measurements like pin gauge is, of course, destructive and time-consuming to perform. Eddy current also has problems with measurements on composite materials, particularly if you're changing from composite materials, which might be um, carbon fiber, and then of course you have to have metal fasteners, and then you have curvature, and this could really throw off the thickness measurements of those methods. Another advantage too is that we've further developed the method, I don't have this here, to essentially use electromagnetic modeling, which allows you to determine the thickness of a single layer without calibration. So essentially you can take it up to any coating and determine what the thickness of that coating is, even without a witness coupon. In the case of, say, a spray robot application, verification has to wait until you've fully cured. This could actually take several days, for 48 hours in some cases. The thickness testing is performed manually. So sensor technologies that can measure wet coatings or curing coatings can be used to predict the final cure state thickness and minimize corrective actions such as sanding overbuilt areas or root coating underbuilt areas. So this is just an example of a case where handheld probes may be used. This can be configured either in a contact. So in this case, where you see this Lyman nose cone, the sensor in the upper left-hand corner has a Lyman nose cone in contact. That's merely for convenience for the operator. If you were measuring a wet coating, you would remove that nose cone and you just move the probe down and it would snapshot the thickness. So the method is very highly accurate and can be used to measure in these complex geometries, as you see here, measuring these coatings applied to an inlet duct in the center of the picture. And then we, of course, have in-process monitoring, where in the upper left-hand corner you see that Class 1 Div 1 sensor mounted to a spray robot, so that it's actually measuring with the concurrently with the spray balloon. So we either measure as the coating is being applied or after the coating has been applied, say at the 90% point. The middle graph shows a coating buildup as many passes, and then say you can measure the change in thickness as the coating may shrink as it dries, and then predict the total coating thickness at different times. This graph just shows sort of a notional diagram of how the in-process spray measurement system is mounted, where you have the sensor at the end of next to the spray gun with the spray robot, and then inside of a paint booth, and then the terahertz control unit and measurement human machine interface inside the non-hazardous control area. Again, this is just showing how repeatable this is here. As you can see that this is in microns of variation, not tens of microns of variation. We have 50,000 measurements of fused quartz. Of course, if you're actually measuring real product, there's far more variation from point to point due to orange peel thickness variations under the spray. This is just a specialty coating measurement, doing a gauge R&R, where we have 3 operators measuring each coupon 3 times with a handheld system. This gave, for example, 10 mil tolerance band gives 9% precision to tolerance ratio with the total gauge of plus or minus 0.15 mils. Again, for those people used to American, we still use thousandth of an inch instead of microns. 1 mil is 25.4 microns. And so this has very low bias and substantially superior to eddy current magnetic gauges. So in head-to-head measurements, the terahertz would often have 40 to 100 times better precision to tolerance ratios. So many of the legacy gauges were just simply inadequate for these measurements. Other kinds of handheld sensor uses here, measurements of tire layer thicknesses inside of blow molded parts, bottles, etc. Here I'm going to show some examples of B-scan type measurements where you are scanning the terahertz waveform over a coating or a surface, and you want to say measure the step and gap or the location of defects with underneath the coating. So the upper right is a sort of a step and gap test area, and the lower the right hand side shows sort of three-dimensional forms where you can see the cross section and B-scan images. One of the applications that we developed was measuring the panel step offsets between two panels that had coatings or boots applied to them. And of course, the coating and boots could be slightly different on both sides. So if you wanted to align the thickness of the underlying outer mold line of the paddles, you could use this to measure the step and gap offset of the panels to adjust them into correct tolerance. Here's another example of B-scan imaging showing defects in plastic panels. So in this case, looking at curved panels and showing the indications of blisters and other defects inside. So in say the top left, you see the top surface, curved surface, and the bottom curved surface, and then indications in the middle of the scan. C-scanning here, the sort of a rolling odometry, essentially takes this B-scanner and you can then paint out images on surfaces. So take the scanner up to the side of an aircraft and look underneath the coatings for corrosion. You can look for the location of hidden fasteners, hidden seams, etc. We've done quite a lot of work with NASA. Again, there's a repetition of the sprayed-on foam insulation imaging, but we did also look a lot at the silica tiles, which are also used on other spacecraft used today. I don't have the whole picture. There's actually a huge composite picture of one whole wing. And what you might not know is that there were actually antennas and other wires underneath those thermal protection tiles. So microwave antennas actually broadcasting and receiving through those tiles. One of the issues was that as these orbiters age, which of course are now museum pieces, NASA actually only knew the location of certain features they might have to access down to about an inch, which meant that in some cases they had to remove more tiles than were necessary. And each tile was tens of thousands of dollars to remove and replace. So in the last dozen or so missions, they did save a lot of money using the terahertz system, and presumably as we go forward with more reusable spacecraft, this can be done as well. This is just a more modern case where they are looking at scanning inside the thermal protection system on the Orion heat shield. So that's a C scanner that's sort of worked up with the terahertz system, looking down at the heat shield that's being applied to the bottom of the spacecraft. Another thing that we've looked at and worked with is an examination of radomes, repairs of radomes, impact damage within radomes. Of course, radomes have to be able to transmit electromagnetic radiation, so they tend to be glass reinforced resin composites as opposed to carbon fiber conductive composites. This is just showing several C scans made at different depths of panels. So depth 1 showing no particular interesting features, depth 2 showing sort of rib structures within the panel, and then sort of a seam structure indication over on the left-hand side. depth 3 actually showing holes and voids that were intentionally put into the panels. And this was actually then automated onto a system to look at C130 panels here, where the terahertz system was integrated into the tool. Here's just another image that we're done with handheld imagers painted together of, let's say, top plies of a radome panel. And then this is some indications where the tap test showed flaws. So oftentimes radomes, you actually just simply tap and look for sound, look and listen for the sound to see if delamination has occurred. There's also many non-aerospace, non-destructive testing applications you may be interested in. We can use spectroscopy, say if you have gases inside of a material, inside of an object. So this is just showing the difference in appearance of a bottle filled with air and a bottle filled with methanol vapor. If we image on the methanol line, absorption line, so you can see that one detects the vapor and the one does not detect the vapor. This was an application where we're imaging for counterfeit detection inside of ICs. So these were complicated system on a chip integrated circuits, and we used high resolution. So this is the case, imaging to detect whether or not the chip as built was as designed, or perhaps some knockoff type chip. Excuse me. Another area is measuring bottle wall thickness, one of the most important things, very important things in reducing manufacturing cost of bottles. Bottles are often made of multiple layers, sort of say 2 outer structural layers and then a thin layer in the middle that is actually the vapor barrier that prevents gases from ingressing or osmosis, getting in and out essentially of the plastic, making the true seal. As you imagine, that the manufacturers want to have enough plastic in each layer, but not too much. It costs money. This is just an example where the bottle is scanned sort of rotationally, showing the outer surface and the inner surface, and then a nylon layer inside the bottle. And here's an example that my colleague thought was interesting, where we were actually examining a layer in the complex molded part and shooting through several other layers kind of at off angles and not measuring there. So it's sort of out of way that you can use the technique to focus on only this spot that you want to measure and ignore other areas of measurement. Here is additional 2D images of this particular part. We have done other sort of non-industrial applications, but sort of looking at art and forensic science with historical objects, looking inside of that, say looking underneath paint to see what was painted underneath frescoes and other paintings. That is not a large or application, but it's very interesting, kind of fun application. So in summary, we can make terahertz measurements of thickness, density, and subsurface images and a wide array of materials and products, primarily with the requirements that they are not conductive, or at least we're measuring the portion of them that are not conductive. The thickness measurement speed, precision, repeatability, and accuracy exceed other types of sensors, particularly non-contact applications. There's no certifications or safety officers required for ionizing radiations. The measurements can be made in very difficult environments, dusty environments, hot environments of hot, just say molded objects. We have deployed nearly 200 systems worldwide, and unlike many other sensors, we can make multiple kind of measurements at once, such as the amount of moisture content and the thickness. And we have many established applications and other applications we're currently developing, and can imagine many more in the future. So with that, I'd be happy to take any questions, and thank you for your time.
Thank you, David. Fascinating to hear there about the technology. It's a new one on me, so I've got a couple of questions just quickly. That perhaps we've got a few in, but I'll field a couple myself as well. I'm just curious. The devices that you supply, are they all off the shelf, or do you bespoke for sort of into other machines, or if integrated, if you know what I mean?
Oh yeah, sure. So actually both. So in the case if you are buying a handheld instrument, that is totally off the shelf. Okay, so you may configure specific options for the type of material you're measuring. Say if you're wanting to measure very thick coatings, you might configure some of the electronic and optical systems different than if you were measuring the thickness of primer down to the bare primer. So from the range of 0 to 4 mils versus 4 mils to 250 mils, but that's all off the shelf. And then we do many systems integration. So when you're looking at, say, okay, now I'm going to put it on a robot arm, then we take the off-the-shelf control unit, off-the-shelf sensors, but there is an integration step where you have to run the cabling, through whatever ducts and conduits and cable tracks, and on the robot, essentially, you figure out where you're going to put the sensor on the robot or the gantry measurement system. Do that, and then interface our measurement system with perhaps what might be an existing process control, process monitoring software system. So in some cases, we do that ourselves, but mostly we work with a number of different other value-added resellers and systems integrators who specialize in, installing the robot and the sensors and all those other pieces, and terahertz being sort of the one part of the measurement process.
Okay, thank you. And just one other question from me quickly. We've got 4 here now, so I'll launch into those just in a moment. I'm right in thinking this is compared to some of the other NDT methods that that you mentioned, ultrasound, etc. And this is slightly newer. Am I right in thinking that it's slightly, or?
Yes, it is. It was probably first developed around 1990, and then we started commercializing in 2000, and I would say around 2010. The technology we developed into sort of outside of laboratory to more industrial, difficult environments where you have, wide ranges of temperatures from, say, 0 to 40 degrees C, and you have humidity, you've got dust and other kinds of things. So all the UL specifications and hardening and kinds of things.
But it seems slightly more robust and straightforward. Perhaps more accessible would be a better way of putting forward to it than some of these other technologies I'm talking about.
Yes, it is. It has its advantages. I would say it's compared to eddy current is more expensive. So there are some very ultrasound, and because of its maturity and eddy current and magnetic methods, because of their maturity, are more ubiquitous and sometimes less costly. So right now, we're kind of going for those really high benefit areas.
Yeah, great. Okay, well, let's take this question from Christophe Riviere first. He wants to know about rust. Have you ever tested your system on rust below paint?
Yes. In fact, we have demonstrated, and others have used our systems. NASA has published a paper on this, being able to detect rust underneath coatings, and rust underneath on pipes, um, underneath sort of the thick kind of composite insulation and protective material they put on pipes. So yes, the answer is yes.
Okay, good stuff. And this next one here from Vinod Sharma, he wants to know how deep terahertz waves can penetrate in a graphite composite material.
Well, that is a great question. Unfortunately, the answer is only about 1 to 2 plies past the resin top layer. So, and the reason for that is that most composites, are often cross-ply sheets of fibers, and you can align if you only have fibers going in one direction. You can align the polarization of the light so that it will penetrate between the fibers. Of course, if you have a cross plies, which is almost always the case, then that's only going to work for one layer, and then it'll reflect off of the subsequent layers. We have done some interesting work, being able to detect impact damage from underneath coatings. So if you have something that hits the coating and then impact damages the fibers, you can see that, of course, but it's limited to sort of those top layers.
Great, thanks for that. This next one here is from Leon Vegas. He would like to know if you can measure an aircraft's top coating on composite materials, substrate with a copper mesh.
Yes, and in fact, that's one of the applications that we have quite a few customers working on. So you can generally measure multiple layers at once. So you might have a top coat, some intermediate coats, and then primers, etc. And then, of course, you hit whatever your conductive layer might be, a copper mesh or aluminum or carbon fiber, and then that's sort of the last layer you could measure. But that probe is not only able to measure once at a time, it's layer at a time. It can be like ultrasound. If you try to imagine that very first graph, if you have multiple different kinds of materials or mixtures of materials, you can measure the thickness of each one separately with one probe, so one time. So essentially, not only you can measure the top coat thickness, you can measure the thickness of everything underneath it until you hit something like that, until you like the copper mesh. But it depends on the size of the copper mesh. If the copper mesh is big enough, the beam's going to go through the holes too. So that's also
Okay, great, thanks. I think you've kind of answered this already from Miroslav Lasek, who wants to know about measuring and finding defects in composite materials. The answer was...
So as long as the composite is something like a non-conductive composite, so glass reinforced, Kevlar, certain ceramic composites, ceramic coatings, turbine, we do a measurement of thickness of YSZ, thermal protection coatings and turbine blades. Yes, you can do that. And we can measure not only thickness, but if you're doing imaging, right, you can then see defects and delaminations, or map the thickness if you want. So it can also look inside the coating to see for bubbles, or look on the substrate for rust, or if it's just a thin sheet of material, or something like a radome that's meant to transmit all the way through, then you can inspect the entire interior of the radome.
Okay, great. Thanks for that, David. We've got a few in a row here from Shyam Sundar Mande. Let's start with the easiest one. Do you have any users in India at all?
Yes, the answer is yes. You have to contact contact us for any references, though. So
okay.
I don't have those offhand.
Yeah. Okay. So you'd also like to know, with your handheld sensors, How do you maintain a constant standoff distance from the object?
Okay, so there's actually two ways. So if you don't mind touching the object, then we add put these little passive nose cones on, so that you just simply put the sensor down onto the surface, and as soon as it touches the surface, it makes a measurement. Now, the height of that nose cone or the thickness of that nose cone does not come into the calculation, actually. It's only there just sort of to aid the user to bring it to the right height. But if you don't need to use that, actually, the other way of using it is you pull the trigger, which sort of arms the device, and then you bring it down, and then when it senses it's in a distance at which you can see a coating, it simply makes a snapshot measurement and reports the thickness then. So if you have a wet coating, you would just hold it over the surface, pull the trigger, and then as you slowly lower it down, it will suddenly make the measurement beep and display the thickness of the coating there when you hit the right distance to the target. And it's not that difficult to accomplish.
Okay, thank you. I'd also like to know about inspecting difficult to access areas, which I thought was a very interesting point of the devices. I mean, who wants to know what the lowest size of the sensor head is you can get to do that?
Yeah, so the smallest sensor that we had there was that Class 1 Div 1, which was designed to kind of be poked around with a robot. And I think we could go a little bit smaller than that, but that's about the size of, it's a bit bigger than a cigarette pack, something like that. So I'm trying to make an analogy of that.
Mm-hmm. Okay, we've got one here from George Thom, who would like to know if you can measure the thickness of a layer when that layer is a mix of different materials.
So yes, there's two ways to do that. So I mean, if the mix is constant, you can just simply calibrate against a series of known thickness. If the mix is not constant, then you would have to use one of our electromagnetic modeling techniques that essentially can look at the amplitude and shape and time of what those reflection series, and then model using dielectric models essentially what that had to have been, which is sort of a unique capability to be able to sort of, even if I don't know what the material is exactly, be able to make a pretty good measurement. That works best with only about one or two layers, but it can be done if you on other layers as well. So yeah, mixtures can be measured.
Okay, thanks. There's one here from Flynn Spears who says, great presentation, and then asks, regarding NASA and launch applications, what work has been done on COPV bottles and what types of defects, disbonds, delaminations, and overwrap thickness increases can be shown?
Yeah, so there has been work on that, and that has been mostly out of NASA Langley. There's a guy there named Eric Muderis, Eric Burke, who you might look up, who have published work on that and look at COPV vessels. Again, depends on the kind of composite overwrap it is. If it's carbon fiber, you're not getting through that. But if it's glass fiber, then you can measure through that. And if you happen to have voids and disbonds in the lamination, you can see those.
Okay, thanks. There's one here from Nagaraju Menshu who says, who wants to know, can it measure the thickness of a layer greater than to the wavelength of terahertz? Perhaps we need to decipher that a little bit, David. I'm not too... Makes sense out of that.
So the answer is that yes. Okay. So there's actually two ways to think about this. So one is what is the precision and accuracy that I can get of a thick layer? Okay. So suppose I have something that's many wavelengths long, and I want to know what's its total thickness. Okay. So this system can measure thickness down to or sort of the phase, as it were, down to like 10,000ths of a wavelength. So you can measure that total thickness of something that's thick very precisely compared to the wavelength. The next thing is, okay, now suppose I have one layer and it's getting smaller and smaller and smaller. So what's the minimum layer thickness can I measure at once? And that depends on the total bandwidth of the system that penetrates through. So that's important because, say, we have between, say, 50 gigahertz and 3,000 gigahertz, then you essentially are measuring with nearly 3,000 total gigahertz worth of bandwidth at once. And then the total bandwidth, if you could think of this sort of a Fourier way, then depends on your thickness resolution. And then that means that a single layer, if you're wanting to resolve a single layer and say, yeah, I've got a single layer, then that works out to be something, if we use electromagnetic modeling, down to about, let's see, half a mil, that's half a thousandth of an inch, that's about 12 microns. So if you were imagining I'm sanding off primer to an aircraft, and then I want to measure, say, what's the thinnest primer that I can measure, it's going to be about 12 microns, and then it'll just look like metal.
Great, thanks, David. Just a few more questions now. Another one from Shyam Sundar. This is quite an interesting one. He would like to know about curved surfaces compared to flat ones. Is there a reduction in accuracy when you're doing curved surfaces?
No, very little reduction in accuracy at all. Because it's a time of flight measurement, unless the curvature is extremely sharp, something like a radius of curvature of a centimeter, which is rare but not unheard of, and we have ways of dealing with that too. But generally speaking, if you're looking at complex curved surfaces on the exterior of your aircraft that has many centimeters of radius and curvature, the accuracy on a flat versus sort of that complex curvature, either concave, convex, is exactly the same. When you get to the tightest curvatures, we do need to take often a reflection measurement off of metal, and sort of as a calibration pulse. And then if you want to measure those really tight curvatures, you just simply make your calibration off of a tight surface, sort of mimics the part that you want to measure, and then you regain any kind of lost accuracy or precision for that measure.
Okay. Good stuff. Thank you. Couple here from Christophe Riviere again. He's got some questions here. How much time does it take to measure a 1 inch square surface, for example? And what is the terahertz frequency range used in your systems?
So terahertz frequency range is, as I said, typically ranges between 50 gigahertz up to 3,000, some very rare cases, 4,500 gigahertz or 4.5 terahertz. Although most of the time, a lot of things only transmit well up to about 1 or 0.8 terahertz. The beam diameter, and this goes back to how long, the beam diameter can range, depending on the focusing system and the frequency that you're operating, anywhere from about 250 microns to 1 millimeter to 2.5 millimeters or larger, depending on the lens systems you use. So, for example, an imaging system, if I did I wanted to have a spot size of 1.5 millimeters and then a square inch. I would be then scanning 1,000 times per second, so 1.5 millimeters square, 1,000 times per second. In the case of our handheld scanners, and I apologize for not showing the video of actually this working, but that kind of paints out a 3-inch by 3-inch image in about a second. So, you're moving along, not super fast rate, but a reasonably fast rate.
Okay, great. Thanks, David. Just these last ones here. What Leon Vegas, he's ready to buy by the looks of things. He wants to know the price of the system.
The prices of the system depend on how you configure them, and I'm going to leave that up to
Let's follow up.
Require because I'd rather not get in trouble with the business and sales guys.
No, there's an aerospace testing discount just yet.
And then ATEX, I saw that question there. That I believe is the equivalent, the EU equivalent of Class 1 Div 1. So you would have to get it certified for ATEX, but essentially, yes, the answer is sent. It could be certified for that.
Sure. Do you want to take this last one from Shyam Sunder, or he wants to know what the typical beam diameter in your case is?
As I said, that depends on how you tune your frequency operating range and the focusing lens you use. But that's anywhere from 250 microns, but more typically between 1 and 2.5, sometimes 5 millimeters, depending on the sensor you want. So for a thickness sensor, we typically use a somewhat larger beam to average out over a slightly larger area. And then for imaging, we try to get the beam tight. It's small features.
Fantastic, thanks. And that last one from Jim there, that I think Priya has just answered about a copy of the presentation. David, I think you'll have Jim's Corellano's email, so you'll be able to get in touch with him afterwards. And of course, the recording is available afterwards on the website, and you'll all be emailed a follow-up email to notify you, and then it will be posted on YouTube eventually. But yeah, David, that was really interesting. I'm really impressed with the way you coped with all of the questions there as well. The audience there really, I really put you through it. So that was really good. Thank you.
You're welcome.
So I don't know if there's anything else you'd like to add before we wrap up.
There are even more applications that we've done here. I encourage you to look at our website and contact me or contact our Terahertz sales and applications group if you have any additional questions, and look for inspiration if it's something that could meet your needs.
Fantastic. Okay, thank you again, David, and thank you everyone that's tuned in live. That's great. Some great questions there. I hope everyone enjoys the rest of their day. Have a good one. Thanks. Bye bye.